All right. Yesterday, during my office hours, actually there were a few students from Signals and Systems, and we had a very good discussion about Fourier series and Fourier transform. And I actually, gave a demonstration of an online web-based spectrum analyzer, and I will share the link with you guys on Piazza later on. But there's a very handy spectrum analyzer that is web based, so you can access it using any web browser, for example Chrome. And I used my microphone as the input, so the audio input. And as I was whistling or talking, I was able to look at the Fourier transform of those certain audio signals in real time. And as I changed the frequency of my whistle, I could see that particular impulse change the frequency. It would scan in the frequency. So, you know, we had a kind of a detailed discussion during office hours on that. So, I will compile certain aspects of that in a asynchronous video lecture, and I will make that available to you. Okay, let's talk about Fourier transform properties. So the first property is kind of a repetition of what we have already seen, but because we are talking about properties formally, I have put this property again. This is the linearity property, and linearity is something that Fourier transform so the Fourier transform operation obeys linearity. And this simply says that if you have a Fourier transform pair, say for example the Fourier transform of x1 of t is cap x 1 of omega, and similarly the Fourier transform of x2 of t is cap x2 of omega, then if you use two scalars a and b, and then you scale x1 by a and you scale x2 by b, the Fourier transform of that resulting weighted signal is going to be a times x1 of omega and b times x2 of omega, cap x2 of omega. So their individual Fourier transforms will get scaled by those same scalars. And the proof is quite simple by definition of Fourier transform. We can consider a new signal x3 of t, which is the scaled and summed version of x1 and x2. Fourier transform of x3 of t is cap x3 of omega. By definition, it is negative infinity to infinity a x1 of t plus b x2 of t. That's where the signal goes. Multiplied by e to the negative j omega t dt. So you integrate out time, you will be left with omega. And because a and b are scalars, they come out of the integration process. You are still integrating over here with respect to time. You're still integrating over here with respect to time. This is simply the Fourier transform of x1, which is cap x1 of omega. This is simply the Fourier transform of x2, cap x2 of omega. So that's a very quick proof of the linearity property. And these two have to be given, right? These two have to be given for that. And you can actually use this in a very handy manner for finding several of your Fourier transforms. Okay. So there seems to be a glitch again. All right. Guys, it looks like I'm going to have to restart the meeting. Please join back at the same link. You guys are able to hear me, right? Yeah. So my screen. Oh, hold on. I think it's just come back up. Okay. All right. I think we can continue in that case. All right, so that's your linearity property. Let's move on to the next one, which is the time shifting property. If you do a particular operation in time domain, you will have some change in the frequency domain. So on the left here, we have the time delay. In this case, not time delay, time shift, right? T0 could be negative, could be positive. So when you have a time delay with respect to your time domain signal, the property says that you essentially multiply a phase term in the frequency domain. So the Fourier transform of x of t, if it was given to us as cap x of omega, then when you shift the signal in time domain, you essentially multiply by e to the negative j omega t0. T0 is the same time that by which you are shifting the signal. So time shift corresponds to a phase term in the frequency domain. Notice the magnitude of x of omega did not change. No change in magnitude. Right? When you delay things, the frequency content doesn't change, only the phase changes. So there is only a change in the phase term. Let's prove it. Start off with this new signal x3 of t, which is the delayed version of x of t, whose Fourier transform we are defining as cap x sub 3 of omega. x3 of omega is the Fourier transform of x3 of t, which is negative infinity to infinity, the delayed version or the shifted version of x. The shift is by t0, e to the negative j omega t dt. So this is the Fourier transform definition. Now I want to get rid of t minus t0. I want to make that one time variable. And the way I can do that is by doing this change of variable where I define tau as t minus t0. So this becomes tau now. So this becomes x of tau. And earlier, t was going from negative infinity to infinity. And now tau equals t minus t0. So tau will also go from negative infinity to infinity. So this change of variable did not change the limits of the integration. But e to the minus j omega t became e to the minus j omega tau plus t0 because of the change of variable. Tau plus t0. t0 is a constant. It is not dependent on tau. So that particular term can be pulled out of the integration. The rest of it remains as is, which is x of tau e to the minus j omega tau d tau, which is essentially the Fourier transform definition. So this is x of omega. So I can color code this as, if this is pink, then this is pink. and that is the blue term. And we can interpret this as time shifts in the time domain result in phase shifts in the frequency domain. No change in magnitude, only change in phase. Now, using the linearity property and the time shifting property, let us try to answer this particular example. So the question over here is, find the Fourier transform of a signal e to the minus 2t plus 1, where negative 2t plus 1 is all of that is in the exponent. Unit step delayed by 2 seconds, 2 time units. Now, there is a simple trick over here that is very helpful. The trick is to manipulate the exponent into a suitable form, because I want this guy, the exponent, to be of the form t minus 2. So what I'll do is I will manipulate this time domain signal as in the form of this. I have e to the minus a times t minus 2 plus b. You see this? This is t minus 2 because that is t minus 2. So that later on I can apply the time shift property to the entire signal at once. So when you try to represent this in that particular form, what are you going to have? When you equate the exponents, e to the minus a times t minus 2 plus b equals whatever this is, right? So all of this equals that, because we are trying to find the a and b that satisfy this. And when you equate the coefficient of t and the constant, you will see that you will have this particular result. A is 2, b is 3. So you can rewrite that particular e to the minus 2t plus 1 term as e to the minus 2t e to the minus 2 times t minus 2 minus 3. And then from before you had u of t minus 2, which will remain as is. Just to quickly summarize, we did this manipulation in this form, minus a times t minus 2 plus b, because we had the unit step at t minus 2, right? So we wanted these two to be the same. That's why we manipulated it this way. Once you manipulate x of t to be this, Fourier transform of this is the same thing as Fourier transform of this. E to the minus 2 times t minus 2 minus 3 u of t minus 2 is the same. So now consider unit operations. So let us start with what we already know, right? That's an earlier result. We did this in the previous lecture. We didn't have 2, we had e to the minus alpha t earlier. So let me just review that result for you guys over here. We said the Fourier transform of e to the minus alpha t u of t is 1 divided by alpha plus j omega when real part of alpha is greater than 0. We derived this result earlier in the previous lecture. So using this Fourier transform pair known result, what I can say is the Fourier transform of e to the minus 2t u of t will be 1 divided by 2 plus j omega. Known result. Now we can do the time shift, because I want this to be t minus 2. I want this to be t minus 2. So you get all the t's are replaced by t minus 2. So when you do a time shift in the time domain, right? The time shift is here, not there. Time shift is here and here. The time shift results in a phase term in the frequency domain. So x of omega remains as is. You have e to the minus j2 omega multiplied to it. So we are getting closer to what we really want. What we really want is Fourier transform of a signal minus 2 times t minus 2 minus 3. So I still am missing e to the minus 3. So if I have e to the minus 3, so I just multiply my time domain signal with that particular term, e to the minus 3. It's a constant. So I multiply e to the minus 3 in the frequency domain as well. That is using linearity, right? So I multiply there, I multiply there. So that's using the linearity property. So by doing all of that, you got this to match up with that, and the Fourier transform of that is right here. E to the minus j2 omega minus 3 divided by 2 plus j omega. Questions about this example and how to use unit operations. First, we used a known result. Then we used the time shifting property. Then we used linearity property. All right, let's erase this guy and let's move on here. Another example of finding the Fourier transform of a signal that looks like an addition of two rectangles. And as you can see over here, one way of doing this is to split it up in this way, decompose into two signals. This guy can be decomposed as one rectangle over here of height 1 from 1 to 4 and another rectangle of height half from 2 to 3. Or you can do it in a few different ways. You can say there are 3 rectangles. One is from 1 to 2, 2 to 3, 3 to 4. No matter which path you take, you will get the same answer for the Fourier transform of this time domain signal. But in this case, it might be easier to work with two signals that are centered at the same point, 2.5. So if it is centered at the same point, 2.5, it will help you in terms of simplification later on. So what we are going to do is we are going to use a reference result. The reference result is the Fourier transform of a rectangle. The Fourier transform of a rectangle is this. Let me draw it over here. Say in black, I can just say, well, maybe not here. I'll do it on a different page. So this is the reference result. For a rectangle, if you have this guy at 1, say this guy at t1, this guy at negative t1, this guy at 0, and you have this as time domain, and this is say x of t, then the Fourier transform of this rectangle, x of omega, cap x of omega is simply going to equal 2t1 sinc omega t1. Or if you want to write it in the form of sine function, you can write that as 2 divided by omega sine omega t1. So sinc x is sine x over x. You can use that to write this in one of these two forms. So that's the reference result we are going to use. Using this reference result in our example, we can say if this is my pulse, height is 1 from -3 divided by 2 to 3 divided by 2, I get the Fourier transform of that as 3 times sinc 3 divided by 2 omega. Now the real question is, why did I use 3 divided by 2? Right? So why use 3 divided by 2? In other words, why use the width of this rectangle to be 3? Right? That's the point here. The width of this guy is 3 time units. Why did I use that? I use that because I want this to be 3 time units, so that I can find this and then apply a time shift property. And similarly, over here, let me do this in blue. Over here, the width is 1, so I choose a width of 1 over here, which is centered at 0, because I know the reference result for a rectangle that is even symmetry, that is centered at 0, that is symmetric about the y-axis. So for that particular rectangle, the narrow rectangle, height is half. So this will scale to half later on, but I'm just using reference result here. So if you have a pulse that is height 1 from -half to half, its Fourier transform is going to be sinc half omega. All right. So using the reference result, we found out the Fourier transform of this guy and this guy as 3 sinc 3 by 2 omega and sinc half omega. Now we know that x of t, the signal x of t, is being written as summation of x1 plus x2. So I can use linearity over here to write the Fourier transforms of x1 and x2. However, I have written x1 in the form of p1, where p1 is my standard result pulse. So what is the relationship between x1 and p1? Well, if I want to go from here to here, I need to delay this signal by 2.5 times, because this guy is right now centered at 0. It needs to center at 2.5. So I need to shift this right, which means delay the signal. Delays the signal by 2.5 time units is what is described over here. Similarly, I also need to delay P2 of t by 2.5 time units to get x2, which is indicated here. So now to summarize, x1 written as the summation of x1 and x2. x1 and x2 are written in the form of known transform pairs in the form of p1 and p2. Also note that we have incorporated the scaling of p2 as half here, because this is 1 but this is half, so we need to adjust that. We took care of that as well. Now all we need is Fourier transform of x, which will be Fourier transform of p1 of t minus 5 by 2 plus half p2 of t minus 5 over 2. Fourier transform of this guy will simply be cap p1 of omega multiplied by e to the negative j omega 5 over 2. And the Fourier transform of this guy is going to equal half cap p2 of omega multiplied by e to the negative j omega 5 over 2. Those two terms are written individually over here. And because we have chosen things symmetric about the same point, which is 2.5, we were able to pull out that common factor of the phase term, e to the minus j 5 over 2 omega, and we are left with a real quantity inside. 3 sinc 3 by 2 omega from the known pairs, right? So that's that guy is right here. And this guy is right here. All right, questions about this. Break the rectangles into signals for which we know the transform pairs, use the standard pairs, apply the properties of time shift, linearity, and then get to what the signal that you want. Questions here? E to the j omega t is only for the time shift. Is that for all cases? When you say all cases, what do you mean by all cases? So if you have a time shift, you will have a e to the a phase term. It could be, minus, meaning like it could be delay, it could be advance, but you will have a, for time shifting, yeah, you don't need to change the transform, right? You see, if you are given that x of t, the Fourier transform is cap x of omega, the Fourier transform did not change. When you shifted the signal from x of t to x of t minus t0, x of omega didn't change. You only had an additional phase term. Does that answer your question, Ryan? Okay, so you can also think of it in this way. Suppose suppose you are finding the, not the finding the, let us suppose you're trying to find the Fourier transform of me talking. Well, whether I talk right now or 10 seconds later, as long as I talk the same thing, it will have the same Fourier transform. It is just that you will have a phase term associated with it, right? It will be the same Fourier transform because the signal is the same. It's just shifted in time, so you have an additional phase in the Fourier frequency domain. All right, let's keep moving here. Reference result, sure. This is also in your properties page, by the way. So now we are revisiting the Fourier transform of the unit step here because formally we have talked about linearity today. So you can express unit step function as the sum of half sine function and half of a constant. So if you add up these two, you get that. We already know the Fourier transform of the sine function, and we already know the Fourier transform of constant. The Fourier transform of a constant is an impulse multiplied by 2 pi. This is from the previous lecture. And the Fourier transform of half sine t is half times 2 divided by j omega. So 2 divided by j omega corresponds to sine t, sine function. And let's see, for a constant, you have 2 pi delta of omega, an impulse in frequency domain, right? This guy doesn't have any frequency. It has DC. It just has an average value. So that's what you see in the frequency domain, an impulse at omega equals 0. So using linearity now, you can say unit step is x1 plus x2. x1 and plus x2 are half sine and half times a constant. So the Fourier transform of the unit step function should be 1 divided by j omega plus pi delta omega. This particular function can also be written in bracket notation, just as you see over here. All right. Let us take a look at a very, very useful property next. I hope while you guys are doing some homework problems on Fourier series, you are realizing that the time derivative property to find the Fourier series coefficients of periodic signals is extremely useful. Whenever you have a linear function or a quadratic or a cubic, you can use the time differentiation property 1 time, 2 times, 3 times, and so on. And all you have to do is track back by dividing the Fourier series coefficients by j omega k. 1 time, 2 times, 3 times, and so on. So it's very, very handy to have that time derivative property for Fourier series. And there's a time differentiation property even for the Fourier transform. When you differentiate a signal in the time domain, you multiply the Fourier transform of the signal by j omega. Patrick says pulse and impulse train are epic. Okay. All right. Agreed. Given the Fourier transform of x of t is x of omega, if I know this, then when I differentiate the signal in time domain, I simply multiply by j omega in the frequency domain. Can I prove this? Well, the proof involves very quick steps. It starts with the definition of inverse Fourier transform. The inverse Fourier transform definition says I can go back from frequency to time domain if I know x of omega. And the time domain signal x of t will simply be 1 divided by 2 pi integration over all omega, so that you have t left, will be x of omega e to the plus j omega t. And actually the position of x of omega over here in the integral, that is what implies that this is a Fourier transform pair. So when you differentiate the signal, say differentiate both sides, and you are differentiating with respect to time. When you differentiate the signal with respect to time, you differentiate that guy with respect to time. What do you have? You will have an additional e to the j omega term. J omega term. You will have an additional j omega. And the position of this highlighted in red will indicate that that is the Fourier transform of the derivative signal. Right? The position term in the square brackets, it is what is telling us that that is the Fourier transform of the signal dx by dt. Differentiate the signal in time domain, you multiply it by j omega in the frequency domain. Notice for this will apply for all transform pairs. You change some aspect of the signal in time domain, there will be a change in the frequency domain. That change, what is that change, is what we are trying to figure out. And it actually works in the other way as well, right? So if there is a change in frequency that you notice, that means that there is a change in the time domain as well, because the arrows point both ways. In other words, if you realize that the Fourier transform of the signal got multiplied by j omega, you know that the signal in time domain got differentiated. Now let me ask you an interesting question here. When we use the time derivative property of the Fourier series, at some point we had to go back. And the way we went back is by dividing by j omega k. You guys remember that? You differentiated the signal. Then at some point, you wanted to find the Fourier transform of the original signal. So you had to divide the Fourier series coefficients by j omega k, so to go back. What will you do here? If you find the Fourier transform of the derivative signal, how will you go back? Integrate, yes. So there is a common mistake here. The common mistake is divide by j omega, right? That's the common mistake. You divide by j omega and you go back. No, you don't go back by that. Omega is now an independent variable, and omega can take the value anywhere between negative infinity to infinity, including 0. So you can't just divide by j omega to go back. What you have to do is integrate the function, which means we also need the time integration property. So in order to go back, we use another property. All right, more about that later. Let us try to find the Fourier transform of an impulse. Oh, that should be easy, right? The Fourier transform of an impulse should be a constant. All frequencies are present in the Fourier transform, in an impulse. But we are trying to use the derivative property in order to prove this or to find this. So find Fourier transform of an impulse, and that impulse is at t0. Let me sketch that out here. Oh, come on. 1, 2, time. And in this case, I have this. Fourier transform. This is delta of t. This is t. This is Fourier transform of delta of t. This is delta of omega. This is omega. And let's see. On the left side, we have an impulse. So we just have this with a weight of 1 at time 0. And the Fourier transform of that is a 1. All frequencies are present. And we are using the time derivative property to show this. The Fourier transform of an impulse can also be written as the Fourier transform of the derivative of the unit step. We already know the Fourier transform of the unit step to be 1 divided by j omega plus pi delta omega. We used linearity to express unit step as the summation of half of the sine function plus half of a constant. So we know the Fourier transform of the let me do it this way. If this is, I use yellow here, and I will use u of t for that, and I will use derivative in a different color. So if I differentiated it in time domain, I multiply by j omega in the frequency domain. And I simply multiply it out, I get 1 plus pi j omega delta of omega. What is pi j omega delta omega? I need to evaluate omega. Pi j omega delta omega will equal pi j 0 delta omega. which will be 0. So you will be left with 1. So what you have is a transform pair for an impulse and a constant over here. So there's the same result as before. All right. Next, let us take a look at time domain convolution property. So omega is 0 is because when you multiply a function with an impulse, you need to evaluate that particular function where the impulse is valid. The impulse is valid only at omega equals 0. So you need to evaluate this guy when omega equals 0. In this case, it'll cancel out because there is an omega right here in the scaling. So you need to evaluate that at the same location at, so for example, if you had pi j omega delta of omega minus 1, this would equal pi j 1 delta of omega minus 1, which would equal pi j delta of omega minus 1. However, over here, the impulse is present at omega equals 0. So you need to evaluate that with respect to omega equals 0. All right. Let me box this up to keep it separate from this. All right. Rectangle, sinc. Differentiation, multiply by j omega. Time shift, phase shift. Convolution in time domain is multiplication in the frequency domain. So one more Fourier transform operation pair, which is one of the most used properties, and this is very helpful to find the response of linear time invariant systems. Because when do you do convolution? You do convolution when you want to essentially find the output of a linear time invariant system using the input along with the impulse response of the system. That's why you do convolution. And if that convolution exercise becomes very tedious, you can also do it in a slightly different manner, which in a different domain. You can actually do a multiplication in the frequency domain, which might be much easier to do. Multiplication is clearly much easier generally compared to convolution. Convolution in time domain results in multiplication in the frequency domain. You might have seen this play out even in the Fourier series properties. What is the property here? The property is if you have two signals, x1 of t, whose Fourier transform is cap x of omega, and you have another signal x2 of t, whose Fourier transform is cap x2 of omega, then in time domain, if you do a convolution, in this case it's going to be a continuous convolution. If you do a time domain convolution, the Fourier transform of the convolved signal will be the product of those individual Fourier transforms. So x1 of omega multiplied with x2 of omega. So the proof next. The proof is going to rely on the definition of Fourier transform. So what we are trying to find out is the Fourier transform of x1 convolved with x2. And because we know that a continuous time convolution is evaluated using a continuous or a convolution integral, we can express that integral right here. So let me color code this as well. This guy right here, convolution is done here and here. And then the Fourier transform brings in this integral along with that. So you have a double integral. The inner integral is with respect to tau. The outer integral is with respect to t. And you can change the order of the integration depending on which signals depend on which integration depends on which variable. So what we are doing over here is, once we change the order of the integration, we are bringing out negative infinity to infinity x1 of tau. This guy only depends on tau, so I can keep that with respect to tau outside. And the first thing that I'll try to evaluate is x2 of t minus tau with e to the minus j omega t dt. And if we look at what this is the Fourier transform of a shifted x2. So Fourier transform of shifted x2 is simply x2 of omega multiplied by e to the negative j omega tau using the time shift property. So this goes back in here. You get integration remains as is, x1 of tau remains as is. Now this has been solved for x2 of omega e to the minus j omega tau d tau. x2 of omega is independent of tau, so that can come out of the integral. You will be left with integration negative infinity to infinity x1 of tau e to the minus j omega tau d tau, which by definition is the Fourier transform of x1 of t. So you are left with just the product of those two Fourier transforms, x1 of omega and x2 of omega. So that's a proof of the time domain convolution property. You do a convolution in time domain, it results or is equivalent to multiplication in the frequency domain. And it actually works the other way as well. We will later on see that if you were to multiply in time domain, it will be a convolution in the frequency domain. Hence the term Fourier transform pairs. Now we said if you want to go back from the time derivative property, then you need to integrate back. So we need integration property for that. The integration property says if you integrate the signal in time domain, then you essentially multiply by 1 divided by j omega plus pi delta omega in the frequency domain. This is given x of t is has a Fourier transform of x of omega. So we are considering this to be x of tau, and you are integrating from negative infinity to t. So when you integrate out tau, you will be left with t. So when you integrate in time domain, you multiply by that factor highlighted in yellow in the frequency domain. That's the integration property. Let us try to prove it. The simplest way to prove it is to use the time domain convolution property that we just looked at. The time domain convolution property says convolution in time domain reflects a multiplication operation in the frequency domain. So now we form x of t convolution, x of t convolved with u of t, unit step. Using the convolution integral, I can write that as negative infinity to infinity x of tau u of t minus tau d tau. U of t minus tau is only valid or it is only non-zero for time between negative infinity to t. So this integral, because all the other times it is 0, so they don't need to be part of the integral. So what you have with this convolution is simply integration from negative infinity to t x of tau d tau, which is your time domain signal for which you are trying to find the Fourier transform. So we have used the unit step over here conveniently to adjust the limits of the integration. Next, When you try to take the Fourier transform of this convolution, what do you have? Simply the Fourier transform of this integration. Because this guy, if that equals this guy, so the Fourier transform of this will equal Fourier transform of this. Take the Fourier transform on both sides. Next, Fourier transform of this is going to equal find the Fourier transform of x multiplied with the Fourier transform of u of t. So you multiply. That's using the time domain convolution property that we just proved. X of omega remains as is. Fourier transform of unit step we had proved earlier. That just comes out to here. 1 divided by j omega plus pi delta omega. So that proves the integration property. When you integrate, notice here over here, when you integrate, you not only divide the signal by j omega, but you also do an addition of plus delta omega. All right. Now, I would like to spend a couple of minutes talking about how you can leverage these properties to find the response of linear time invariant systems. So first, I have made two worlds. The first world is time domain world, and the next one is the frequency domain world. So everything that you see above this line is a time domain. Let me make it really broad here. Right. So above that line, we are in the time domain. Below that line, we are in the frequency domain. And we have three signals essentially. We have the input indicated by x of t, whose Fourier transform we are writing as x of omega in the frequency world, frequency domain. We have the impulse response of the linear time invariant system as h of t, whose Fourier transform we are writing as h of omega, cap h of omega. We have the output of the system indicated by y of t. We are writing the Fourier transform of that using cap y of omega. So these are all Fourier transforms. Oh, too much. Fourier transform, Fourier transform, Fourier transform. Now, in order to find the output, what are your choices? In most cases, generally, you will be after y of t, right? And y of t, you can reach y of t in two different ways, generally. One way is this. Maybe I can use green for this. No, I want to use a bad color. Maybe a pink for this. All right. One way to reach y of t is this. What is that? That is work in time domain. Meaning, perform the continuous convolution. That's one option. That might not be the best option. Another option is this. What is that? That is, go to frequency domain, multiply, find inverse Fourier transform. So actually we have, instead of doing one operation, we are doing three operations. but that actually might be simpler in some cases. So depending on which way is simpler, more elegant, is convenient, use that path. So let me describe the second option a little bit more in detail. Go to frequency domain. So that's step number 1. Finding the Fourier transform of X, finding the Fourier transform of H. Once you have the Fourier transforms of input and the impulse response, multiply them. So that's the second step. Multiply them to find the Fourier transform of the output. Then the last step is, because you want to actually go back to time domain, you take the inverse Fourier transform. Yes, exactly like that. If the time domain is easier, should we still go into frequency? Not necessary, right? If the time domain is easier, all right. Let me take an example here. Let me take an example of, let us suppose you had a rectangle here and a rectangle here. If you had input as rectangle and impulse response as a rectangle function in time domain, which approach will you take? The pink one or the green one? Time domain, absolutely, because it is much easier to convolve two rectangles than to do this. Sinc. Multiply sincs, you get sinc squared. Find the inverse Fourier transform of a sinc squared, right? So if the two rectangles are the same, then you get sinc squared. But if they are not the same, then you get sinc times sinc. And then you are trying to take the inverse Fourier transform of that. You guys see that? So one approach might be better than the other depending on what signals you have available to you. So in this particular case with rectangle, working in the time domain might be the best choice, a convenient choice. But in some cases, some other cases, finding the Fourier transform once, the second time, multiplying, and then taking the inverse Fourier transform might work out better in some cases. For example, what if I switched this around? I'm trying to give an example where the other way is better. I will say sinc here and sinc here. When I choose sinc functions for x of t and h of t in time domain, convolving the two sincs might actually be very difficult. It might turn out to be very, very difficult. But if I go to the frequency domain, I will have a rectangle here, I will have a rectangle here, I will multiply the rectangles, I will get another rectangle here, and then I will try to take the inverse Fourier transform of that, which will be a sinc. Might be very, very easy for me when I do that. Right? So the green path is easier now. To work in the frequency domain is easier in this case. All right, let me erase this so that there's no confusion later on. But I hope you see that depending on the type of the signal, which world you work in might be the best choice. All right, questions about this discussion on response of linear time invariant systems. Now, believe me when I say this, I've been harping about there is an easier way to do these problems. There is an easier way to do these problems. You don't have to get buried with the math. Try to do it in an easier manner. You can see that apply in this discussion very significantly. If you happen to choose the wrong domain to work in, you might spend unnecessary amounts of time, really, really long time, and still not get the right answer. So please spend some time trying to think about how do your steps look like. Try to play out the math in your head for a few seconds. That will give you the idea to work which domain you should work with. Okay, here we are doing an example. Next, find the output y of t for an LTI system. You are given the input as e to the minus t u of t, and you're also given that the impulse response of this LTI system is e to the minus t u of t. Can you guys think about a system that looks like that? An LTI system whose impulse response is e to the minus t u of t. Anyone? I'm just going to make up one. Do you guys agree with that? RL, sure. You can go for RL. I just went for an RC circuit with R as 1, and yeah, absolutely. So I just chose an RC. I could have chosen R as half ohm and C as 1 farad. But I think choosing a smaller capacitor is a little bit more practical than 1 farad. So I at least reduce the insanity by half. So I have a half farad capacitor and a 1 ohm resistor. And this is my input and output, right? That's essentially, that will give you this impulse response, e to the minus t u of t. And I know that because e to the minus t divided by tau u of t, right? So that I know the response based on the decay. If I give it an impulse, e to the minus t divided by tau, where tau is R times C for a RC filter. Anyway, coming back to this. This discussion is sort of going to make sense more for the people who are electrical engineers and who have taken circuits. But that's not necessary for us to go forward. For us to go forward, I really need to look at the signals in time domain. I have e to the minus t u of t. I have e to the minus 2t u of t. I want to find out the output y of t. And in this case, I'm using the frequency domain. I'm working in the frequency domain. So I'm taking the green path here. Is the pink path very difficult? No, probably not. You have two exponentials. The continuous time convolution is also pretty easy to do in this case, but we are trying to show the green path here. So this is an example where both paths are easy. What is the Fourier transform of the input? Use the standard property. We had e to the minus alpha t u of t. The result for that was what? 1 divided by alpha plus j omega, with real part of alpha greater than 0. So we have used that particular standard property here. All right, fine. We have used that property over here to write x of omega, which is the Fourier transform of x of t, as 1 divided by alpha plus j omega, 1 plus j omega. And the Fourier transform of the impulse response here, also called as the transfer function, which is the Fourier transform of impulse response, which is 1 divided by 2 plus j omega. You multiply the signals now. Convolution in time domain, multiplication in the frequency domain. Multiply them. Once you multiply, you need to use partial fractions expansion to separate them out into two known transform pairs. More about standard partial fraction expansions later in the class. Right now, just assume that I've done this right. So I've multiplied them and I spread them out into did partial fraction expansion on that. Then you simply go back, find the inverse Fourier transform of this guy, right? Find the inverse Fourier transform of this minus find the inverse Fourier transform of that, which is written out over here. When you find the inverse Fourier transform of y of omega, that will simply give you e to the minus t minus e to the minus 2t u of t. So there are two Fourier transforms, one multiplication and one inverse Fourier transform operation that was involved in this. The other option would simply be e to the minus t u of t convolved with e to the minus 2t u of t. And you will get the same result. I've just shown you an alternate way. Could you go back to the partial? Yeah, absolutely. All right. Next, I have this signal here. I'm trying to find the Fourier transform of a signal which is t between -1 and 1, and it is 0 otherwise. So it is t, a linear function with a slope of 1 between -1 and 1, but all the other times it is 0. Maybe I can highlight that, and that. Now, when you see a linear function, what comes to mind? When you see lines, what property do you are you very tempted to use? I see a linear function, I'm tempted to use a differential property. Yes, time derivative property. And the reason is this. As soon as I differentiate x of t, I will have a rectangle. And I know the Fourier transform of a rectangle. It is a standard result. So whenever you see lines, linear function, you straight off, you know that time derivative property is going to be extremely beneficial in that case. So let's try to do that. Take the derivative of x of t in cases you have linear functions. After differentiation, you will have pulses, or you may also have delta functions. But delta functions are pretty easy to handle. Why? We already know the Fourier transform of that. So if they are located at different times, we simply use the time shift property and we'll be okay. So when you differentiate the signal in time domain, so here you have x. You recognize it's a linear function, so you differentiate x. When you differentiate x, we are calling that y. A slope of 1 between -1 and 1. That will give you a line, a straight line between -1 and 1. And there are two discontinuities. Both those discontinuities are pointing down. So you will have an impulse at 1. You will also have an impulse at -1. the weight of those two impulses will be -1. So now y of t can be written as the summation of three signals. Let us color code this. Maybe some part of it is in yellow. That is my p of t. Known result. The second one is my impulse. The impulse is at -1. So that's that. Then the third one is an impulse at +1. That is that. So I've simply written up y of t as a summation of p of t, which is a pulse for which I know the Fourier transform from a standard Fourier transform pair, and there is an impulse, and there is an impulse shifted right, and there is an impulse shifted left. So I would need the Fourier transforms of that as well. Now take a look at this. P of t is simply a rectangle between -1 and 1 of height 1. It looks like that. Using the Fourier transform pair, the reference result, I know that cap p of omega is 2 sinc omega. I'm done with that piece. Next, I need the Fourier transform of impulses. So what is the Fourier transform of delta of t? Let me write it over here. Maybe I can write it in blue. Let's see. Delta, too big. Delta of t. What is the Fourier transform of that? 1. We know that. So what is the Fourier transform of t minus 1? Time shift property. 1 times e to the negative j omega times 1. Delta of t plus 1. What is the Fourier transform of that? 1 times e to the plus j omega times 1. Now, I actually need minus, right? So I will draw minus there. That is means minus here. Minus there. So that means minus here. Fourier transform, Fourier transform, Fourier transform. All I'm using is the time shifting properties. And of course, the Fourier transform of an impulse. Now, using that, I know the Fourier transform of y of t now, right? Fourier transform of y of t is simply y of omega, which is the Fourier transform of p of t plus delta of, minus delta of t plus 1 minus delta of t minus 1. So I have to write their individual Fourier transforms. I've got p of omega minus 1 times e to the plus j omega minus 1 times e to the minus j omega. We discussed that earlier. Now, p of omega is simply 2 sinc omega. This is from here. And the remaining two complex exponentials can be simplified using Euler's identity as negative 2 times cosine omega. These two have been simplified to write as negative 2 times cosine omega using Euler's. So we are there. We've got y of omega. What do we need? Fourier transform of x. So now you need to integrate back. Let me write that in bold here. Integrate back. to get Fourier transform of x of t. So how does that look like? Well, x of t is the integration of y of tau d tau, right? Because x of t and y of t had a derivative, so you have to go back by integrating y of t. So that means that x of omega, the Fourier transform of x of omega, should be the multiplication of y of omega from earlier with this. And this comes from the integration property. This is also the Fourier transform of the step function. So we have used the integration property here. Time integration property. Y of omega, substitute from before, the remaining terms also known, and once we do that, you see you have 1 divided by j omega y of omega, but you also have pi delta omega y of omega, right? Pi delta omega y of omega. But because you have an impulse, you have to evaluate y of omega at omega equals 0. Omega equals 0 is what? 2 sinc 0 minus 2 cosine 0. That is simply going to be 0. So that will cancel out. You will be left with 2 divided by j omega sinc omega minus cosine omega. That is the Fourier transform of x. So just to recap, what did we do? The moment we realized that it's a linear function, we tried to use the time derivative property. We differentiated the signal. We got impulses, and some rectangles. We know the standard pairs for pulses and impulses. We used the standard Fourier transform pairs along with linearity property and time shift property as and when necessary. Then we put together the Fourier transform of the derivative of the signal. Once we have that, to go back, we need to use the integration property and then simplify as needed to get your answer. Sinc omega is 1, absolutely right. Yes. Sinc x is sine x over x. Use L'Hopital rule, you get sine x over x. When you use L'Hopital rule, you get cosine x over 1. You know what to do with that now. Next property is frequency shift property. If you can have a time shift, you can also have a frequency shift. So what happens when you have a frequency shift? Well, if you have a frequency shift, you essentially multiply by e to the j omega naught t in the time domain. I hope you see that there is a duality relationship that is at play here. Whatever you do in one domain almost has a similar effect in the other domain. So when we meet again later, next week, you will see a new property which is called the duality property. Duality exists between time and frequency. So let's try to prove this frequency shift property. If I shift in frequency, I change the time function by multiplying it with e to the j plus j, right? Earlier you had a minus j. Now you have a plus j. Omega naught is simply the amount of frequency shift times t. This is also given x of t, the Fourier transform of that is cap x of omega. So given that when you shift in frequency, you multiply by e to the j omega naught t. Proof: the Fourier transform of e to the j omega naught t x of t is simply by using the definition of Fourier transform, negative infinity to infinity, e to the j omega naught t x of t, all of that function, right here, e to the minus j omega t dt remains as is from the definition of Fourier transform. Next, I'm going to combine the two exponentials to write them this way. And this is simply omega evaluated at omega minus omega naught. So you can define omega minus omega naught as omega prime, and you get cap x of omega prime. That's the Fourier transform. So that proves the frequency shift property. Let us try to find the inverse Fourier transform of x of omega. We are given that in frequency, x of omega is 2 pi delta of omega minus omega naught. What is the Fourier transform of that? Well, in the previous lecture, we found the inverse Fourier transform of 2 pi delta of omega. We did that by definition in the previous lecture. If we know that the inverse Fourier transform of 2 pi delta of omega is 1, this guy is in time domain, right? When you apply the frequency shift property, what do you have? 2 pi times delta of omega minus omega naught will be 1 multiplied by, so this is also in the time domain, 1 multiplied by e to the j omega naught t. So we can say that the Fourier transform of e to the j omega naught t is simply 2 pi delta of omega minus omega naught. So now we have another Fourier transform pair, e to the j omega naught t. The Fourier transform of that is 2 pi delta of omega minus omega naught. So the weight of this impulse in frequency is 2 pi, and that impulse is located at omega equals omega naught. Now using this, we can actually find the Fourier transform of a cosine. The Fourier transform of a cosine can be obtained by using the property that we just wrote right here, e to the j omega naught t. Because I can construct a cosine using Euler's as cosine omega naught t is e to the j omega naught t plus e to the minus j omega naught t divided by 2. For each term, I can write its Fourier transform because linearity applies for Fourier transform. So for this term, I've got the Fourier transform here. For this term, I've got the Fourier transform here. Two impulses, one at plus omega naught, the other at minus omega naught, where omega naught is essentially the fundamental frequency of the cosine. So if x of t is cosine omega naught t, which looks like this, where that is the time period, 2 pi divided by omega naught, then the Fourier transform of the cosine is consisting of two impulses. One guy is at plus omega naught. Oh no, this guy is blue, this guy is yellow. Both of them have a weight of pi. Using this, we can actually go further. We can write these two Fourier transforms. The Fourier transform of a cosine is pi delta of omega minus omega naught plus delta of omega plus omega naught. And similarly, if we had applied this Euler's identity in order to take this towards a sine function, then we can also write sine omega naught t is pi divided by j, impulse at minus omega naught minus impulse at plus omega naught. Sorry, I should say this is at plus omega naught, this is at minus omega naught. So that gives you the Fourier transform of a cosine and a sine function. Let us come back to this later on. Okay, so what I'm going to do next is actually let us spend some time talking about this, right? The Fourier transform of the cosine and the sine function. So let me start with this. going to bring back my so let us see if I can share content here. I think I can. Are you guys able to see my screen now? All right. So we said that, you know, the Fourier transform of the cosine is there are two impulses. So what I'm using right now is a web-based spectrum analyzer. It's also a signal generator. On the back end, the script is Java-based. I'm going to use this particular screen here. This is going to essentially be the output of the spectrum analyzer, or I can switch it to the oscilloscope or the signal generator view as well. I have multiple options here. I can use a signal generator. I can use a microphone. I can use the source to be right. Ethan has pointed out the link. If you guys want to copy the link and open it up, that will be helpful. Now, what I'm going to do is, you know, I have two domains, right? Time and frequency. So if I change my signal source to a microphone, and now as I speak, you can see that the signal is changing level, right? So suppose I want to slow things down. What I'll do is this. I will try to increase the time for which I'm looking at it. So I'll say, okay, I want to take a look at a longer time, 21.33 milliseconds each. Can I go? That's it. That's how far I can go. Actually, let me use more samples, 32,768 samples. All right. Now you can see as I speak, you can see the signal show up on the screen. So essentially, I'm using this as an oscilloscope right now, in real time. So if this is the time domain view, let us play a few games. I can create an impulse, and I can show you the impulse right here. So that was just me clapping, sort of mimicking what an impulse is. And you saw some impulse response, and that impulse response was essentially the impulse response of my microphone, right? Whatever is between me and this web-based spectrum analyzer, all of that is a linear time invariant system. Assuming that it is a linear time invariant system, what you saw on the screen was the impulse response, you know, mainly of my microphone. Again, right? So it goes up and down instantly. Okay, so that's what is happening in terms of time. And if I whistle, or if I play a tune on a musical instrument, what am I doing? I'm creating a note. So I'm essentially producing a clean audio signal that will have one frequency essentially. So I'm going to try to whistle, and I'm going to try to observe what kind of signal I see on the oscilloscope. Notice over here, everything is time domain right now. Maybe too many values here. So let me slow things down. I hope you see that as I whistle, it is appearing as a sinusoid on the screen in time domain. So depending on, so based on our discussion right now, in frequency, if I whistle, there should be only one tone. So let's try to see that. So I'm going to shift this the view from time domain to frequency domain. So I have the frequency now, and I'm looking at 0 hertz all the way to 24 kilohertz on my screen now. And what you're seeing right now is a real-time measurement of the Fourier transform of my speech. And let us see what happens when I whistle. By definition, it should give me one or it should technically give me two impulses. One is at plus omega naught and the other is at minus omega naught. But there are no negative frequencies on this scale, so you should technically see only one impulse. And as I change the frequency of my whistle, that impulse should move around in the frequency domain. Right now, we are observing frequency domain. Axis is omega. So as I was at least attempting to change the frequency of my whistle. I hope you saw that impulse move around in the frequency domain, because I was changing where that impulse is. All right. So in fact, you can also play other things with this, right? So this right now is taking the input from my microphone. I can take the signal source from the signal generator, and right now the signal is nothing, right? It's a sine wave. So it's giving me one impulse at the frequency of the sine wave. But if I went to square wave, notice what happens. The moment I went to square wave, I see all the harmonics. I see all my Fourier series coefficients present at 1 omega naught, 2 omega naught, 3 omega naught, and so on. And the strength or the magnitude and phase of each of those Fourier series coefficients, that is what our A sub 1, 2, 3 are. And you can see the Fourier series coefficients of triangle, of a sawtooth waveform, and so on. For a sine, you only have one on the positive side, right? That is the amplitude of A sub 1 plus 1. Let's see. Can I do something else here? Oh, maybe this is it for now. All right. So I encourage you guys to play with this. You can also use your phone to generate musical notes and try to track the frequency information. All right, I'm gonna stop the recording here. Actually, stop sharing first, and stop the recording.